Hello and welcome to Lecture 4 in our probability review for Bayesian machine learning. In this lecture, we'll talk about expectation and moments of random variables. In this lecture, we will talk about two moments of random variables. The first is the first moment, otherwise known as the mean, and the second one is the second moment about the mean, otherwise known as the variance. So in order to derive moments, we need to use the expectation operator or find the expectation of a random variable. For the discrete random variable case, this uses a summation operator. So we take the random variable, for the first moment, we take the random variable and multiply it times the probabilities in the probability mass function over all possible values that the random variable can take on, and that returns our expectation. So for example, if we have a random variable with three values, 0, 1, and 2, and the probability of each one of those values is 1/3, we take the expectation as 0 times 1/3, plus 1 times 1/3, plus 2 times 1/3, which returns a value of 1. So the expected value for that random variable is 1. For the Bernoulli case, the expected value is given by the parameter p. For the binomial case, it's given by n times p. For the Poisson case, it's just the parameter, which is lambda. For continuous random variables, the difference is instead of using a summation operator, we use an integral, and we integrate over the entire real space. So we take the random variable, multiply it times its probability density function, and then we integrate to find the expected value. The uniform case is the easiest one to see since it's just a box on the real line. So for example, a uniform between A and B is just going to be the sum of A and B divided by 2. So there's the expected value of a uniform random variable. The expected value for a beta random variable is the parameter A over A plus B. The gamma is alpha over lambda. The Gaussian is just the parameter mu. And the t-distribution is mu only if the degrees of freedom are greater than 1. Actually, if the degrees of freedom, if nu is equal to 1, then there is no expected value in the t-distribution. And that, if you recall, is a Cauchy distribution. So that is an interesting distribution in that it has no expected value. The expectation of the function of a random variable is easy to compute. If we have a real valued function, say g, in the discrete case, we just take that function over our random variable and multiply it times the probability at each point in the probability mass function. In the continuous case, it's the same thing, except we don't have a summation, we have an integral. You can use this to find what's known as the third moment of a random variable, or the expected value of x cubed, the third moment. And for a uniform random variable between 0 and 1, see if you can do the integration and show that that's equal to 1/4. Okay, the second moment about the mean is called the variance. And the variance is defined as the value of the random variable minus its expected value, the first moment, that quantity squared. So this is a function of a random variable, as you can see. And in this case, it has a set of special properties that we will use. The variance is a way to measure dispersion about the mean, and that's why we use it. For the Bernoulli case, the variance is just p times 1 minus p. The binomial case, it's n times p times 1 minus p. The Poisson case, it again is just lambda. So in the Poisson, the mean and variance are equal to the same thing, the parameter of the Poisson. The variance of a continuous random variable is defined identically to the discrete case, except that we've replaced the sum with an integral. The uniform is given by the sum of the two parameters, the two extreme values in the uniform, a plus b over 12. The beta, it's given by ab over a plus b squared, a plus b plus 1. Gamma, it's alpha over lambda squared. The Gaussian, it's the second parameter in the Gaussian, which is given the name sigma squared. And for the t-distribution, it's sigma hat squared times the degrees of freedom nu over nu minus 2. And this only exists if the degrees of freedom are greater than 2. So the t-distribution, it doesn't have a mean if nu is equal to 1, and it doesn't have a variance if nu is 2 or 1. So the t-distribution only has a mean variance for values of the degrees of freedom parameter greater than 2. There are two useful formulas that we use when we talk about the variance. The first one is we define the standard deviation as just the square root of the variance. And the second one gives us a way to compute the second moment. The second moment is simply equal to the square of the first moment plus the variance. And in the next lecture, we'll look at multivariate distributions.